The theme today is the intersection between the science of brain function and the engineering of machines. How can we learn from brains to build better machines? How can we capitalize on the exciting progress in machine learning to better understand brain function? So I think the order is going to be Tommy, and then Josh, and then Jim, with an initial introduction of about 5 minutes each. And then we'll turn it over for discussion between the three of them, and also questions and comments from the audience. Tommy.
Thanks, Gabriel. So this idea came up because CBMM was started as centered, focused on the science and the engineering of intelligence. That's something we came up, the original founder, especially Josh and me, and now it's 7 years or so that have passed. So it's kind of interesting, I think, to have a discussion about where we stand. And just to set the rules of the game, we're not trying to define science or engineering. What we mean with science and engineering, this is just a definition of words. So it's not very useful to try to change that. The definition we adopted is science as natural science, so defined by the object of study. So the object of study of science, apropos intelligence, is human brain, human intelligence, maybe animal intelligence. And the object of study of engineering are computing machines. So these are just definitions, correspond to the standard definition according to which, for instance, chemistry and physics and neuroscience are in the School of Science, and computer science is in the School of Engineering. It's just a definition of the object of study, of the interest. Does not have anything to do with rigor or depth. We all agree that science and engineering are both equally important. They must be rigorous, they must be deep. You know, depending on your taste, or whether you are on the party of Aristotle or on the party of Plato, you can, according to this definition, put mathematics in the School of Science or the School of Engineering. So I don't buy. But both science and engineering need mathematics, obviously, and the rigor of modern science. So, so that's something we should all agree. The other thing that is important for CBMM, and is that I hope everybody at CBMM agrees, is that we believe that if we want to understand human intelligence ultimately, which means how our brain computes intelligence, then we need to combine the science of the brain and the engineering of machines. We need everything to go forward. And of course, we need to do experiments on the brain, human behavior. So the idea of this meeting was, of this discussion, was to go beyond this and address related questions, which are much less clear than just the definition I gave you. Things like whether we need to understand human intelligence in order to build intelligent machines. Or maybe vice versa. Maybe we need to build first intelligent machines in order to understand human intelligence. We don't know. We can discuss about it. Back when we started CBMM with Josh and others in 2012, we could at the time claim that neuroscience of visual cortex had led to models of visual recognition like neoconitron, HMAX, and so on, that were state-of-the-art for computer vision. They were a new inspiration for computer vision, very different from the computer vision algorithms. But in the meantime, things have changed and the pendulum have perhaps swung back. Now it seems that models that come from engineering are actually good models of the brain, as it turned out. And so is that going to continue this way with neuroscience just testing engineering models, or there is we can expect another phase in which neuroscience will suggest to engineer a rather different type of models from the ones that are in vogue today? So there are many such questions. I want just to stop here, not to take too much time. Hope people will bring many of these interesting questions up. And in the meantime, I'll pass the microphone, the screen to Josh.
Okay, thanks. So yeah, I'll also try to speak very quickly just to give other people mostly what I'd like to hear is other people's perspectives here. Tommy talked about the pendulum swinging back and forth between, I guess, two poles, both of which are ones that I think we're all in CBMM very interested and committed to and working on. One is the idea that the science of intelligence, how it arises in the mind and brain, can inform engineering and can guide engineering of more human-like kinds of AI systems. And the other is that the engineering tools that are being developed can inform and guide our science, in the spirit that Tommy has long worked with and worked out with David Marr, and that has inspired many of us. We think in CBMM about our science as reverse engineering. We're trying to come to understandings of how the brain and the mind work in the same terms that engineers would use to build those systems. So, that's that tradition of bidirectional interchange between those fields is really, I think, what we're all about. But it does seem to be that sometimes the most promising directions go one direction or the other direction, as Tommy said. The perspective, I guess I would just add, which comes from my experience in my lab, where we primarily work on the mind level, on the cognitive science level, although increasingly we are really interested in CBMM has really opened this up for me in a really significant way, making contact with the brain level, is that actually it seems that the pendulum might be swinging in different directions at those different levels in a way that is really interesting and positive and synergistic, right? So as Tommy referred to, there's been a great progress. I think Jim will talk more about this. His lab has been at the forefront of leading this in applying recent developments from in particular deep convolutional neural nets to understand the ventral stream. Nancy's lab has been using these in all sorts of really interesting ways as well, and many others here. So that's a place where it seems like the engineering is in some ways kind of guiding the science now in terms of studying the neural basis of vision. But on the cognitive level, I find actually in my lab these days, most of what we seem to do is kind of cognitively guided AI. Honestly, I wish there were more people in our lab who were really working on the cognitive science, the study of human behavior and what it tells us about the mind, where the action seems to be right now is using cognitive science to guide AI to make more human-like forms of AI, right? I have many people, whether coming to our lab, whether they've been working in neural networks or robotics or computer vision or natural language processing, and sort of asking us, okay, well, what have you learned or what has your field learned about how computations underlie cognition that we can use to make neural networks or make AI smarter, right? Because we know we've achieved a lot, and yet we still, mostly have systems that solve pattern recognition problems and use mechanisms of function approximation, and there's something missing, maybe something quite big missing. And how can computational cognitive science guide that? So I see us being in different projects in our group. We are both using, I'd say let's specifically focus on neurally based or neurally inspired engineering tools like neural networks. We're both on the cognitive level using non-neural network ideas, like ideas from probabilistic inference and symbolic representations and so on, to try to guide and improve together with neural networks, the AI side. But then I'm also involved in projects looking at vision, but also language in the brain, where we're using neural networks, today's best engineering tools, to try to understand how the brain works. And I think that's really interesting, that it has the promise, in a sense, you know, the engineering, reverse engineering process might be a little bit out of phase at the mind level and at the brain level, where it might be that, you know, if in neuroscience, science has the most to gain from engineering, but in cognitive science, the science has a lot to contribute to engineering, then by swinging back and forth at those two levels, that might be a way that we can actually bridge the cognitive and neural levels, because it still is the great, I think, outstanding question for us in our field, is how does the mind work in the brain, or how does the brain give rise to the mind? And I think, again, most, if not all of us would agree that if we only work at the level of models framed in terms of words and intuitive concepts, we're not going to be able to do that, because the language and the intuitions and the classical vocabularies of cognitive science and neuroscience are too far apart. But if we can translate our insights about cognition into engineering terms, and we can translate engineering terms into real biological neuroscience insights, then that can be a way to use the mathematics and the formal tools of engineering to make a bridge between the higher and lower levels of explanation, or the, you know, the more, at least, mind and brain levels of explanation. I don't mean to imply any particular vertical ordering, but you guys know what I mean. To link up those levels of analysis and I think it may be our best shot for doing that. I'll just point to one concrete research direction, which maybe people might want to talk about later, which is work that I've been very involved with in a very indirect, or I don't know, secondary capacity. The main work is done in Ev Fedorenko's lab and by Martin Schrimpf, who's one of Jim's students, but he's working on language, models of language in the brain, together with Ev and Nancy Kamwisher and me and a number of others. And, you know, basically what Martin has done together with Ev is to show that to take a wide range of state-of-the-art artificial neural networks for language, especially these transformer models like BERT and GPT, if people are familiar with this, but these are the artificial neural networks that have been most responsible for transformative changes in natural language processing from the last year or two, and test these together with earlier generations of neural networks as accounts of language processing from the word up to the sentence level in experiments that Ev and colleagues have done for a while, and really shown great strides basically have come recently. I won't go into the details of this work, although if you're interested, you could read Martin's paper on bioRxiv, but have really shown that, you know, that especially these transformer-based models, especially actually the GPT-2 model, which is the one from OpenAI, which has been, I think, getting the most attention, especially in sort of natural language generation. These models of predictive processing, basically models that are trained to predict what word is going to come next given the previous context, have are really basically by far the best computational models of language processing as measured in either fMRI or ECOG data. And I think that's very exciting. I think that it's by no means a complete account of how language works in the brain, but it kind of, together with work that people like Roger Levy especially have done, and earlier work from Ted Gibson here and many others, not just at MIT, studying behaviorally, showing that basically sentence processing can be, and online measures of sentence processing, like in reading time, can be really well predicted by predictive language models, just like n-gram models or probabilistic grammar models. And now we have like the best predictive language models that have ever been built with these neural transformer-based models. The picture that emerges when you connect behavior, computation, and the brain there is really exciting. It suggests a unifying paradigm coming into play, like an account of language in the brain that might start to rival how we understand vision in the brain. At the same time, that picture also leaves out a huge amount, which is basically, we know that those models, you know, in some sense they predict language, but they don't really understand language. They don't explain how language grounds in perception. They can't turn into an embodied agent. And, you know, they say a lot of, I mean, they do amazing things, and yet it's very clear that they don't really have common sense, or they make all sorts of errors. I'm not going to go into those here. So in other work that we do, we talk to people in natural language processing, and we're talking about how can we take insights from other aspects of cognition, common sense reasoning, language grounded in perception, where we have non-neural network models, and take those and use those to make better engineering language models. And so we see these as just different parts of different steps in this process of the pendulum swinging back and forth, trying to learn from what's unfolded over now a couple of decades in the study of the visual system, and seeing, okay, can we carry that same process of engineering and reverse engineering maybe even now faster because we've learned a little bit how to do it, but into other cognitive domains such as language. So I'll just leave it at that as one example of where I see these things going, and turn it over to Jim.
Okay, thanks, Josh and Tommy. I just want to say up front, I don't think Tommy or Josh and I disagree on things broadly, but more in common than disagreement. But I think for this discussion, it'd be fun to find the points of disagreement. But I mostly want to hear from other people and how they're thinking. This is just a broader discussion. I also want to say that Josh's comments, I don't deserve any credit for the cool things he mentioned that Martin Schrimpf is doing in my lab. I'm just lucky enough to have him in my lab. But thank you, Josh, for mentioning Martin's work. So now let me just sort of give you guys 3 minutes on my overview of kind of how I think about science and engineering. Many of you heard this before, but for those of you who haven't, I just to lay it out there. Let's take our goal as a community. Maybe not everybody in this room or this call wants to do this. The goal is to understand the mechanisms of natural intelligence. That's not everybody's goal in the world. Let's just if we just take that as a goal. We could discuss whether that's a good goal, but I'm going to just take that as a given goal. What does that mean, mechanisms of intelligence? That means there's questions about the mind that are explained in the biophysics of neurons and their connections. That's what it would mean, at least to me, to have a mechanistic model of intelligence, intelligence being an aspect of the mind. So if you accept all that so far, how are we going to actually do that if we get real about it? Okay, now we have assumptions. Do we think that the accurate assumptions are going to be more complex than the two main types of tools we've used in science for building our hypotheses? My assumption is yes. In other words, it is going to be more complex than word models that we typically use. Word models might be things like the brain is a prediction engine or things of that sort. And it's going to be more complex than elegant mathematical equations, simple mathematical equations. So we're going to have complex models to explain natural intelligence. I hope most of you agree with that, but let's assume, I'm just going to take that as an assumption that we have complex models as hypotheses on how you go from neurons to intelligence. So that's usually going to have to be described in some language that we can transfer among humans. And right now, the best language is language of code or maybe hardware or some combination thereof. So we're going to have a hypothesis space that's complicated. And how are we going to proceed as a species to build hypotheses in that space? We need a process. We need to build hypotheses, and then we have to test them against data. So far, hopefully, you can find the weaknesses in my assumptions, but so far I don't know where they are. So then when you get to that point, the only question you have is, who's going to build these things and what data are we going to test them against? Those become the operational questions. And I don't care if we call those people scientists that build them or engineers or companies, but somebody has to build them because they're complicated and we need them. Otherwise, we don't actually have anything to test against data. So I'm agnostic about what we call that, again, whether that's engineering, science, I don't care. But we have to build things. And that must be done, and the hypotheses must be built, and they must be tested against data. And that's really just science to me in understanding natural intelligence at the mechanistic level. And so that's all I wanted to say, big picture. And I just want to add for Tommy's question about, do we need to understand human intelligence to build intelligent machines? To me, that's sort of a non-question. How could we ever say we understood human intelligence if we couldn't build it, right? So it always is going to have to be that we're going to have to build intelligent systems before we really understand natural intelligence. I'll just say that's a natural corollary of what I just described there. And I'm going to end it at that and leave it as sort of points of discussion. If people want to attack my logic, I would love to respond to that, but I want to let this be a discussion. So I think that's just an opening position for me. So I'm going to end there. Thank you, guys.
Okay, so thank you very much, everyone. I want to emphasize that we want to hear from all of you, so don't be shy. I don't see any hands here. So maybe one question. I'll start, but I really want to see. Okay, now as I was about to start, I see Nick Roy raised his hand. So Nick, go ahead.
Yeah, great, thank you. So it's true that your three positions are very similar. So I want to sort of make a hypothesis and get your reactions to it. Maybe it's a couple of hypotheses. So first hypothesis is that it is true that in intelligence, science and engineering, they've talked to each other, but they haven't done a great job of really sort of leveraging on each other's strengths. So that's hypothesis one, which I guess we could argue about. But the more interesting hypothesis to me is that I think the reason that the science and engineering have not really engaged each other is because they think about the world in fundamentally different ways that are important. That engineering, to a large extent, is the act of putting things together. There was a thing from Jerry in the chat about an engineer creates that which never was. And to create something, you basically have to compose things together. So you have to figure out how things go together in new and stable and useful ways. Science tends to be a bit more reductionist and just trying to figure out what the thing is and not thinking so much about the interfaces. Josh, you made a really a nice point about, like, sort of figuring out the connection between the different layers of sort of representation. But I don't know that the science of natural intelligence has really focused hard at, like, what are the compositional interfaces that let us take pieces of the architecture and put them together? I can't take a piece of GPT-2 and plug it into a new architecture and expect it to work in a predictable way without having to retrain. So in that sense, it's not composable. So I guess my hypothesis is that level of compositionality has been missing from our knowledge or understanding of how the brain actually works. And how do we get it? What are the experiments that we can do to figure out what the interfaces are that give us more compositionality of the pieces of the brain?
Well, I guess I can try to respond to some of those things. Yeah, I mean, I agree with you in terms of on the science side, but I guess maybe that's partly the kind of work that I've been trying to do, and we're especially excited to do. So, some of this is work that we have done using what people these days are calling like a neurosymbolic interface. So together with, initially with Judge Wu, who was a student in our group and part of CBMM and is now a faculty member at Stanford, but also with Jiayan Mao, who's a relatively new PhD student, and a number of others, Chong Gan and some people from the MIT IBM lab. Antonio Torralba has been part of these things. We've built various kinds of neurosymbolic models that basically try to do at some very limited kinds of grounded language, and they combine, like, basically something much simpler than GPT, but like a stacked LSTM sort of language parser that parses a question or a statement into a symbolic semantic parse, and then sort of like basically a neural image interpreter that segments and de-renders an image into a symbolic scene graph, and then a reasoning engine which applies the symbolic sentence parse onto the symbolic scene parse to answer questions or talk about scenes. And that was just one example. We've done static and dynamic stimuli. These are examples of things where we're trying to build systems that put the pieces together, guided by some ideas about cognitive architecture, which people have studied, like people like Ray Jackendoff have studied these ideas for many years, as understanding the interface between language and perception, but not actually built models of these things that can run on images. And so we're trying to basically be inspired by some intuitions from cognitive science to build these systems. But I agree that I think, a lot of, especially today's neural networks, they're really good when they're on data that looks like what they were trained on. But to have composability and generalizability, strong generalization outside of a training set is very tough. Those systems that I was just talking about don't do that. But here's where I think some of the probabilistic programming-based systems that, like, Vikash Mansinga's group has been working on, and we're working with him on using these in various kind of common sense reasoning and building machine common sense projects. I think you have both composability and strong generalization. There are other engineering challenges and scientific challenges that those things face, but we think by combining these, basically by exploring in an engineering sense, guided by scientific questions of exactly the kinds that you're asking, the neurosymbolic and the probabilistic programming, and those can even come together into a probabilistic neurosymbolic toolkit. I think I see this as a way forward that's going to be valuable for both the science and the engineering. But it's big challenges. I mean, you're exactly right to point to the challenges that really neither the scientists nor the engineers, I think, have addressed that well.
Long ago, David Marr made famous this metaphor of levels of understanding a complex system like a computer and the brain at different levels. You can understand the computer. You can say, I understand the computer because you know how to use PowerPoint, without knowing anything about logical units in the computers or nothing at all about how transistors work. And you can understand how transistors work and know nothing about the software. And these are all valuable ways of understanding a system. With David, we stressed the fact that these levels are kind of separate, modular. That's related to Nick's point. But if you go back, and this was really for political scientific reasons at the time, it was because we thought that neuroscientists did not understand the computational algorithmic level, and it was important to stress the existence of that. But if you look at the history of this, of what David Marr wrote, the history of that is a paper we wrote together about levels. And that in turn came from an earlier paper I wrote about the fly, where there were levels of understanding. Instead of the computational level, there was a behavioral level. And David correctly, replaced that with a level of essentially characterizing a problem and its possible solutions, the computational level. But the other thing that got lost in translation was the fact that in the work in the fly, we stressed with Werner Reichert the fact that in the brain, unlike a computer, these levels of understanding are quite tight together. You cannot really understand how circuits work without knowing details of transmitters and synapses and so on. And I think, in modern time, people took too much at heart the computational level. It's not enough for having a theory of the brain. It's important to have a theory at different levels or models that can be tested and falsified at different levels. Not only, at some higher level. For instance, if you have a model using neural network, you should really ask, how can neuron implement an RLU? Does that exist in the brain? How could it possibly be? Otherwise, this model is not biologically plausible, not even falsifiable. And so with other things, like, of course, gradient descent and backpropagation and so on. So I think if you are examining an engineering system, because it was made up by engineers and teams of engineers, you will find much more separation between the levels of understanding than you would find in a brain. Evolution did not have the luxury of doing that. And we have to take this into account when we develop, biologically plausible models of the brain.
I was just going to agree completely with Tommy's last point that engineers we had to find levels of abstraction and compositionality just to manage the complexity. But there is a hope that evolution had to sort of also work with choices of gene replications that would then be composable. So it just might not be in the language we're used to talking about. So there's still some hope. It's not as if it's completely non-compositional, but I think it wouldn't be in the MAR levels, as Tommy said. It's going to be in some other form of how do I replicate a few genes and build another level of cortical loops, another cortex is cortex is cortex. These are the natural things we see that might be the composable pieces that evolution is working with. And it's the engineer in this sense, right? By engineering by trial and error, so to speak. And that's our only hope there, if we really want to say the brain version, at least to me. Anyway, thank you.
So I just wish we knew the objective function that was being optimized there. That would be wonderful to learn.
Survive and reproduce.
Survival.
I think it's actually essential for understanding to be able to break problems into pieces, break systems up into parts, and understand how those parts fit together. And that's so that the scientific understanding is going to be essentially what looks like an engineering understanding too. I mean, that's always been true for very complex systems. Real difference between science and engineering has nothing to do with the tools used. Every engineer investigates the materials he works with. Every scientist builds equipment to do his experiments. The honest answer is that it's really a question about what the goals are, but the mechanisms of thinking that are required for doing both are the same, and they're basically decomposition of a system into parts that you understand how they're put together to perform the to have the behavior that's observed.
Okay, thank you. We're going to move on to the next question by Mashid.
Hi, I hope you can hear me well. Can you hear
Yes.
me?
Yes.
Okay, great. So thank you all for this discussion panel. I just wanted to know your opinion on a top-down approach to achieving intelligent approaches like knowledge representation and reasoning. Could you comment more on that part instead of a bottom-up approach?
I guess I could comment on that, at least of the official panelists. I'm not exactly sure what you have in mind, but I mean, I guess very broadly, that is a lot of what we do in our group. So we come from the cognitive science side, and a lot of what we do is we try to develop, formal frameworks for knowledge representation and reasoning. That might be probabilistic inference. It might be some kind of symbolic or probabilistic programs, which combine many of the powerful features of abstraction that you get from symbolic language and flexibility, ability to deal with uncertainty that you get from probability. And there's always uncertainty when you're learning from sparse data or few examples, or in the ambiguity that confronts natural science or natural intelligence in the world. So that I think of that broadly as a knowledge representation and reasoning thesis that has been very successful in modeling many aspects of cognition at the computational level. I think there's issues of modularity that really come up in human knowledge. It's part of how cognitive scientists have understood how humans achieve flexible reasoning and broad generalization. And so that's the toolkit by which we do that. But then there are really big questions of how does that work in the brain? What are the neural mechanisms, either in the level of single neurons or networks of neurons or within single neurons? They're great mysteries about how these formalisms or computational tools for knowledge representation and reasoning that have been successful at the cognitive level and explain and predict a lot of behavior and really explain it in terms of underlying general principles we can make sense of. A lot of what we're looking for is really there in the cognitive level, but how that works in the brain is a great mystery. And part of why I'm really interested in studying language and language in the brain is because it's a way into that. I also think there are aspects of common sense scene understanding. This is something that Jim and I and others, like especially with Dan Yeamans and Nancy, people in Nancy's lab too, are interested in. I think we can also get at some basic aspects of knowledge representation just in trying to take our models of vision in the brain and going beyond what Jim has studied with so-called core object recognition, where you're just recognizing or categorizing a single object, to trying to understand a whole scene, the relations, like the object, these objects are on the table, these ones are balanced or not balanced, this object is contained inside that one. So understanding multi-object scenes and their relations, that's also a very basic kind of, I think, symbolic knowledge representation. And whether it's through trying to understand the neural basis of sentence meaning and understanding, or the neural basis of compositional scene structure, we think those are ways that we can start to understand these things in the brain. And it's broadly top down in that we have models that work to a certain degree at the cognitive level and fit behavior. And then we're, in a reductionist way, trying to say, okay, now how might these pieces be implemented in neurons? Maybe we'll posit some kind of things that look sort of like neural networks, but aren't very much like anything we currently understand in the brain. And then that will pose a further challenge. Maybe there's new things we have to discover in biology. Maybe we need to adjust those engineering mechanisms. For example, the transformer models, which have been so successful in natural language processing, they're really different from how we understand neurons in the brain. Is that a fundamental thing? Is that just a compactness for getting certain things to work in GPU memory? We don't really know. But that's broadly a top-down approach driven in the way that I think you're suggesting.
Actually, a general understanding will always involve both top-down and bottom-up understandings, which connect together at some point. And then
I absolutely agree. Yeah.
Just a follow-up question, if you don't mind. Do you have any favorite method that you have used probably in knowledge representation reasoning? Like we have semantic networks, we have inference graphs, we have Bayesian networks, we have concept graphs, hypergraphs. Is there any of them
people who know me, we've used various things. The graph representations have a lot of value, and they look a little bit more like neurons than some other symbolic approaches or neural networks. But I am a big fan of probabilistic programs and probabilistic programming. I won't go into it here, but I think this is a this is a toolkit that generalizes, subsumes and generalizes a lot of other classic knowledge representation ideas, but especially really allows us to combine the power of abstraction that you don't just get in graphs, but like higher order, you need higher order logic or full, recursive programming languages. Like, I'm very inspired by Jerry's work in using Lisp and Scheme to try to think about the structure of intelligence. And some of the first probabilistic programming languages that we built in our group, Vikash Mansinga and Noah Goodman, who's now at Stanford, built, they took basically the ideas of knowledge representation and reasoning that Jerry and colleagues had worked out, but embedded that in a framework for probabilistic inference in a language called Church. And that was just the beginning of what's become a really fertile program, developing these tools on the engineering side, and we're trying to apply them on the science side as well.
Josh, I think you'd agree that that level of model of that language is like, say, thermodynamics in physics. So it's at best a phenomenological description.
Yeah, or it might be like the level. It might be like the level of algorithms and data structures in computer science.
Maybe, but what I'm saying, you have to make a connection to the brain.
Exactly. That's why I'm saying, to do that, I'm looking to apply these models in the places where I see right now we can make the best connection. So that includes scene understanding, at the, vision going beyond.
I also mean developing models, theories of how neurons could compute those kind of.
Absolutely.
We all agree. Yeah.
Yeah. I mean, but again, I think we all agree, but we're also all know that we don't know where to look for those ideas. So I think, like, again, everybody who hasn't read Jerry's book on the structure and interpretation of computer programs should read that as a classic example of crossing levels on the engineering side, and trying to cross between the sort of algorithm data structure and circuit levels. And that's one way to go. Another way to go is to look at these neurosymbolic models, which are, or like graph neural networks that, these are things that are coming from the modern neural network toolkit that's trying to give you a language for implementing these kinds of things too. And those are just two of several possibilities. Yeah.
Gosh, if you look at the history of physics, thermodynamics was speaking about quantities like entropy and heat without any idea of what they were.
Yeah.
And only later that, mechanical statistics, Brownian motion and so on, they gave a mechanistic interpretation and much more power in terms of what to do with them. And electricity was the same story. People used built engines, generators, batteries, without really understanding what electricity was, having some kind of fluid analogy. It was when Maxwell came around, then there was a real understanding of electromagnetism, and Maxwell reverse engineered electricity, to use this term of Jim I don't like, because that's science. Scientists never use the reverse engineering, but anyway.
I think Tommy, here
engineering electricity, and then out of it came radio, telegraph, computers, the internet, everything, right?
Yeah, no, I think here we'll probably be in a lot of agreement. I think, the top-down route unfolds over time, and we often understand things at a certain more macro level before we understand how those things are implemented, and but the macro level gives important guidance for the underlying micro theories.
In fact, it's interesting that thermodynamics came first.
Yeah, exactly. I mean, so I think, like, Chomsky used to make this point in his philosophy class that I remember going to as a grad student here, that in physics, usually that's how things go. You start with like phenomena that everybody can appreciate, like everybody, like, oh, there's a moon out there and there's some planets and they seem to be moving. How are they moving, right? Or I dropped this apple and it falls. Why does it drop? You start with phenomena like that, and then you come up with mathematical descriptions that unify things at that level, and then you start looking for reducing things down and searching. Sometimes it takes a few years, sometimes it takes a few centuries to come up with the micro level mechanisms. And I think the cognitive and neurosciences seem to also follow that trajectory.
Agreed. Yes.
Okay, we have unless Jim wants to say anything, we're going to move on to a few more questions that we have from the audience. We have Sam next.
Hi, actually, the thing that I wanted to ask fits very nicely in this dialogue. I think that many of us would agree in some sense with Tommy that we should look to the brain for insight into how to build intelligent machines. But I mean, the place where I kind of struggle, and I think a lot of people struggle, is what exactly about the brain matters and what doesn't matter. I think that if you look at where engineers start to scratch their heads when they try to read the neuroscience textbooks and derive something useful from that, is that there's just tons of details that seem irrelevant or even possibly detrimental to building an effective machine. And I think that's true not just for the biology, but also for the psychology. Like if you open up a psychology textbook, there's all sorts of biases or apparent biases that people exhibit. And I think many engineers, while they would like to be able to emulate the intelligence that the people do, I think they would be perplexed if you ask them to implement all the weird stuff that people do in addition. And so how do you know what matters? And I think this is not just a philosophical question, because I think that, I guess I perceive a kind of widget model of neuroscience inspired AI right now, where somebody reads about something that neurons do, like consolidation, and then, or some particular kind of spike timing dependent plasticity rule, and then they just sort of slot that into their model and then see if it works. And sometimes maybe it does, sometimes it doesn't, but that seems like a very inefficient way to make progress if you just by trial and error try everything that biology throws at you. So I'd be curious to hear what you guys think about that.
I would chime in here, Sam. I completely agree with that point. I call that neuro branding. It's all over the place. Like you have an idea, there's always something you can point to in the brain that says, well, the brain does that, so I should do this in my model. But it's the combination of all the things in the brain measured as behavior and neural activity that is all the constraints that have to be brought to bear. And that's kind of where this brain score platform or that comes from for us, that it's not one thing, that's just inspiration. But then there's the point that you also mentioned, which is there's myriad details. So how do you know which things to pay attention to? And brain science doesn't have that answer. So the only practical answer I give is if you choose a top-down problem. Josh mentioned vision, that's what we do. You start with that, then you build models of that roughly in the style of neurons, and then you look in detail and say, well, it's so far is it matching? And that helps you sort out what details matter and which don't. But it's the top-down approach that then lets you sort out what matters and for what reason. But I think it's a mistake to think neuroscience textbooks are going to tell AI how to build something. I'm certainly not in here saying, I hope people don't take my position as being, let's look to the brain and that will be how we figure out how to build AI. I think of it more of the opposite, of building engineered systems that try to do AI as hypotheses for how the brain works. And
well, Jim, can I pick up on that for a second? So if you take I think brain score is a really interesting example, because how do you decide what goes into brain score? Why aren't we taking like the tertiary structure of ion channels into account when we compute brain score, right? There's some heuristic.
Yeah, the practical answer is you can't build models at that level of complexity and get them to run right now. So somebody's got a comment in the chat right now, like we can't build a sun or things like that. There's certain things that we just can't build. So that's one answer to that. But then the rest of it is we don't know. So it's a political answer, which is a bunch of neuroscientists have measured these things. And since they bothered to spend animals and money on it, well, you should put them in because maybe there's some value there until we later learn there isn't. But I agree with you. We don't know the right answer. So our biases put everything in for now. But that's a hard task. So
that's what I'm asking. Is it, if you could, would you put everything in? Would that make sense?
You'd like everything that's, you could just choose the level of your measurement and say, you know, I put in things that apply at that level of measurement. You mentioned ion channels. We're not measuring ion channels. Then you don't put it in a model.
No, but if you were measuring ion channels, would you put them into brain score? That's what I'm asking.
Well, that's the art more than science. This is Josh's comment about you go from big to small. You don't try to bridge all those levels all at once, you know, and I think that's too big of an ask. But again, that's a practical answer of just going from mind phenomena to neural spikes is one level, but it's not the whole answer. And that's kind of where your question is going. I mean, you just got to break it off a piece at a time. You don't solve all the physics from one day either. That was what Tommy and Josh said too. So you're just making practical choices along the way is how I think of that. But they're guided by the tools you have at the time, not by a truth.
Mm-hmm. Next we have Mike West.
So Jim formulated our goal as understanding natural intelligence or understanding intelligent behavior. And Josh proposed trying to translate cognitive science descriptions into engineering terms. And people have been talking about, you know, what how we bridge macro level phenomena with the micro level explanations, and Josh said how we start with the most universally agreed upon phenomena in whatever field it is. And so there's different ways I could ask this question, but it seems to me that the most universally agreed upon phenomena in terms of the intelligence of our brain is the distinction between our conscious and our unconscious brain states and conscious or unconscious processing. And so one question is, do we think consciousness is relevant to understanding intelligence? Do you all think consciousness is relevant to understanding intelligence? And if so, how can we translate that conscious unconscious distinction into engineering terms? Thanks.
Well, consciousness is still a mystery, right?
Right, but it's like the statistical mechanics level description that we would hope to fill in with micro level physics, but it seems that we leave that out of all of our theorizing, or a lot of our theorizing about our model making.
Here is a question to everybody. I'm curious. You all know a Turing test. Suppose, you are called to say whether something in the room you cannot see has human level intelligence or not. You can speak, interact, ask questions, and so on. So to me, this is still the best definition, not very satisfactory, but the best definition of human intelligence. Now, do you think that if I make a test for consciousness, a Turing test for consciousness, would that be the same as the one for intelligence or not? So the question is, now you can interact with something or somebody, and you have to say, is it conscious or not? Is it going to be a different Turing test with different answers from the one for intelligence? I'm curious what people think about.
I think it's a different test. I think an intelligence test is kind of an arbitrary test that's relative to some particular task, like interpreting a visual scene. Whereas the distinction between whether a brain state is conscious or not seems like an actual, objective fact.
Yeah. Can we make a poll, Gabriel?
So for people who are interested in this question, I think Tommy expressed his opinion during the summer course, and you can watch the video. And then we have lectures from Christoph Koch, who has a completely different opinion on this. So you're welcome to join us and watch those videos as well. So the question is whether a Turing test for intelligence is the same as a Turing test for consciousness. That's the poll that Tommy wants to.
Just to be explicit, Christoph thinks no. I think yes. So.
Wait, so say the question then, please.
The question is, if we have a Turing test for consciousness, is the same thing as a Turing test for intelligence. In other words, can you have human intelligence without human consciousness and human consciousness without human intelligence? I think those two things are equivalent. Maybe Tony would
and it's human intelligence in a broad sense, not specific to some topics.
Tommy, you're losing this one. It's all nose in the window.
Can I offer a form of this question? The engineer's version is, if you had a system that could pass Tommy's intelligence test, would it be easy to make it pass the consciousness test? Like that. I think the answer is clearly yes, but maybe people think no. But
okay, so here's the quick poll. So you should see the poll on your screen now. Thank you, Chris, for creating this. So if you can just submit your quick. I like these polls. Maybe we should have a few more questions that
I actually think that the concept consciousness is a funny one. Okay, and that in fact it's one can actually decide whether or not something is like me. That is, I can talk to it, and it acts and it behaves in such a way that I could interpret as being, I could feel that I was like that. But I don't have any idea whether or not consciousness is a subjective impression, and I don't see that there's any way to test for it at all.
So as you all know, the way we're going to decide funding for the next 10 years in the field is by doing polls. So depending on how people, no, I'm just kidding here. So it's 81% no and 19% yes. I don't know what the N is for now. Okay, Arturo, go ahead.
That is very interesting, and I don't know if my question is going to tie up to that, but hopefully it does. So there's been a lot of discussion, especially at the beginning. I wish I would have asked this sooner about, you know, science versus engineering, and I'm pretty sure almost all of us here in our training were trained somewhat funnily either as a scientist or an engineer in undergrad. Like we did something in, for example, biomedical engineering, mechanical engineering, maybe someone did pure psychology, someone did pure cognitive science or neuroscience. And somehow along the way, paths diverted and, you know, everyone kind of became a bit more interdisciplinary. So do you guys think that in the future, like it's happening now already, that there's like a 6-9 cognition computation major, that there's going to be a new PhD major that is at something like a science of intelligence field, or there's going to be something like, you know, mechanical engineering, for example, 50, 60 years ago, everyone was studying turbines, and electric engineers were studying transformers, like the real transformers on the outside, like the power grids. But now mechanical engineering has evolved to another thing, right? So now it's controls, everyone learns circuits. So how do you guys see the future in terms of education-wise at the graduate level even, for the intersection of understanding intelligence and maybe having more interdisciplinary psychologists and computer scientists? Well, what are your thoughts in general? Or do you think it's going to be separated? They're never going to there's never going to be a new department that does kind of.
This is John Barras. I will quote a famous provost of MIT from several generations ago, that you can't separate the two. If you do, you make a big mistake. You can guess who that person was, but he was from MIT.
I mean, I think all of us in CBMM are committed to there being that kind of interdisciplinary field that you're talking about, and we've been working on it. I guess I don't think that means the other enterprises are going to go away. There's scientific questions about the brain that whatever today's engineering toolkit is or tomorrow's one are not necessarily especially well posed to answer. And similarly, there's engineering challenges that are not necessarily want to be informed or have any good reason to be informed by the science of intelligence. But there's that intersection that is where we think the most exciting action is, and where I think many of us think the future of both fields ultimately has come from in the past. Like that's in the past, that's where the future came from, and in the future, that's also where the future will came from, is people who are trying to do exactly what you're saying, who were trained, whatever it was, as a psychologist or a neuroscientist or an engineer, but were motivated by questions that are at the intersection, and so tried to do work that met the challenges at the intersection. And that's where many, if not all of the best ideas in the field have come from.
I think the intersection is inescapable for a very simple reason. To understand the brain, you have to make measurements. To make proper measurements, you need engineering, and then you can go and create science. So because of that, which is also was transparent in physics,
but you have to go the engineering of intelligence, though.
You have to go.
Right.
You have to go back and forth, because just postulating a theory without validating is not the scientific approach, right?
Sure. Yeah, but maybe to be a little controversial, but yeah, I mean, neuroscience, both neuroscience and cognitive science have always had methodologically, they've used engineering tools, but those aren't necessarily the same engineering tools, you know, like building amplifiers or something, or
of course not,
or doing, you know, so yeah, they're not the same engineering tools needed to understand intelligence. And sometimes the field has been held back. I see this both in neuroscience and in cognitive science, just as Sam said. I think both fields are guilty of this. And it's a structural guilt, not an individual guilt, that, you know, people learn a certain engineering tool set just to get their work done, and then they kind of maybe mistakenly overgeneralize and think, well, that's what intelligence should look like, right?
Yeah, I want to make a comment then, because I've got another meeting, but if you allow me, okay. I mean, Tommy knows what I think, but basically, what you need to do is to get some qualitative principles out of human intelligence and see to what extent you can come close to incorporate them in whatever you call artificial systems or whatever. My prediction in the end is that whatever we end up calling provably artificial intelligence, it may not necessarily be anthropomorphic at all. And there are many examples in science that this has happened before. So you learn things like the importance of learning, fine, but then you have to go beyond. You learn, and what do you do with what you learn? You organize concepts, you compact knowledge. We haven't addressed these questions. How do you present rules? How you have to be able to compact? How you connect this to time? Where is attention mechanism? All of these things are qualitative properties of the brain that we understand pieces of them. We have to start putting them into something that we're building, and hopefully we'll come to something that we call artificial intelligence. My prediction is that it won't be anything near human intelligence. And I'll close by saying, for those of you who do not know it, go read the famous theorem of free will, and don't laugh. That's a mathematical theorem from Institute for Advanced Study, and it connects measurements to quantum mechanics and brains. I enjoyed the discussion, and I have to go.
Thank you very much. Thank you. We have a question from Elias Blake, and I apologize to everyone if I'm mispronouncing your names.
No, that's perfect. Pronounce my name perfectly. So I have a question about what the goal even is. And it will tie back though. So Jim named this goal, which I like, a mechanistic understanding of natural intelligence. And we have this other goal, which is that perhaps the objective function that gives rise to intelligence is this surviving and reproducing, right? That's a good goal. Well, I have a question on surviving and reproducing, because I want intelligence that's smart enough not to destroy itself, okay? And at that rate, humans don't seem all that smart. Humans actually seem like we're running our society in some ways into the ground. And so you can ask, well, what would it take for an intelligence to be smart enough to sort of solve these collective action problems like climate change and other things? But it ties back. And so I wonder if seeing these two different goals as perhaps the same goal can be helpful, because in the same sense that humans have a collective action problem of this join or die mentality, neurons and cells have the very same situation of join or die. And perhaps that's what gives rise to multicellular life, is to see that cells can come together and form an intelligent organism, and that organism will survive better than the single-celled organisms would have. And so that the same way that life comes out of multicellular cooperation may be the same very principle that by which humans have to start cooperating. And maybe that's sort of the intelligence that happens everywhere from the most basic to the most complex of organisms. So the real question is, do you guys think that these two different, that unifying those two views is useful?
Well, I would just say that I think, of course, some mathematics would apply at both levels, but I don't think, we don't have an existence proof of a species that hasn't won't destroy itself. We don't know that's true for us, but we have an instance proof of, we don't have machines that do things that we do. So it may not be achievable, but it's a nice goal that you're imagining. But again, we don't know if it's possible. Maybe theory could tell us that, but that's my first answer to this question. But I want to use your question to just kind of pivot to say, somebody asked about, future of, brain and cognitive sciences and future of electrical engineering or computer. Brain and cognitive sciences will not survive if it does not adopt the thing that someone's calling 6-9. It will become like alchemy. That's a strong position to take, but I'm currently the head, and I'm going to kind of take that position. So that if we do not adopt that, we will not survive in the long run. But electrical engineering and computer science will survive regardless of brain and cognitive sciences. So that's not a symmetry there. Somebody said, oh, EECS, or Josh said something like that. It doesn't need, but science, if we don't put that engineering activity into our sciences, we will become like alchemy. And that's what I'm afraid of. And that graduate students have to be trained in that. And that was back to the question of training. And that may be too strong of an alarm to sound at this stage, but I honestly believe some version of that is what we have.
But Jim, I also think that's important. I raised that question. I think that's important in the future for computer scientists too, right? Because now you see in computer vision that everyone just throws a wacky random thing to a deep net, and it's the next, and the objective is state of the art. It's not really forming a theory of learning or understanding a network architecture, whatever it is, right? So sure, it's propelled an entire field forward.
I think
in other fields.
Yeah, but I think you should. Oh, go ahead, Jim. Yeah.
But that goal is not to understand natural intelligence. So again, if the goal is to understand natural intelligence, then you're going to need these engineering things. So, but I don't disagree with, of course, you can build stuff, and that's kind of amplifying my point that people will do that forever, and they will have departments around them. But the natural science of intelligence kind of, you know, is a more fragile thing. I think that's where I'm kind of more resonant with Josh and Tommy. Is like, how are we going to go forward in that regime? And that's kind of why I oriented that goal. It's not the only goal in the world. It's just one that I thought this group was most oriented around.
Yeah, I mean, Jim, I think, you know, BCS has always, even back before it was called BCS, stood for that kind of view, right? That's why, you know, David Marr was here and Tommy came here, and, you know, people did robotics in earlier generations, and, you know, some of the very, even when it was still called the Department of Psychology, there were people using engineering tools, going back to Teuber's vision. So I think we're all bought into that. You know, I think, but I agree with you that like the quest to understand the brain and the mind and intelligence, if it doesn't continue to keep renewing itself with more powerful engineering ideas, tools, and so on, it will run aground, right? And I think we've seen that in the past, and I agree with you. I think we will see that. Other kinds of neuroscience, like to try to cure diseases, you know, might not need those tools. They might be much benefited from them, but they might not need them in quite the same way. But, you know, that's the quest to actually understand intelligence definitely needs them. And I think you see the same thing on the engineering side, because I think you can distinguish EECS from AI, right? In fact, AI was just carved out from EECS. I mean, this might be a controversial view, but I think part of the reason why AI has had a series of springs and winters, right, is because, or where do you get the winters from? Is like at some point, you know, some breakthrough idea comes in, and then you like pursue it to its logical conclusion and you scale it up as far as it can go. But since you made some big, great promise about human intelligence and you don't have the whole story, then you disappoint expectations and you temporarily die or wither. I think CS and EE and ECS can do fine without the brain, but AI needs it just as much as the science of intelligence needs the engineering. That is to keep the really long-term vision of artificial intelligence as everybody has always wanted to understand it. For a long time from now, I think it's going to need to keep looking to natural intelligence to guide, to set the problems, to provide ideas about how to approach things. That's where the new ideas have come from, whether it was neural network people inspired by the brain, or Judea Pearl, who is inspired by human causal inference, right? You know, or, you know, so many people, I think, different. I mean, look at like Boole, for example, as in Boolean logic, right? He introduced many of the, you know, new ideas effectively into computer science before there even was such a thing. He was inspired by the mind, right? That's why his book was called, you know, an investigation into the laws of thought, right? And it starts off reading like a cognitive science book. So, you know, for a long time, I think in the past and in the future, that's, you know, that's where things have come from and will continue to come from.
And just as a quick last thing, yeah, I agree that you probably don't need the brain science for the engineering stuff, but I do think that there's something about the way of thinking that we're all taking for granted here, that it's not that all engineers, for example, know how to run a control experiment or know what they're looking for when they design something. So I think that way of thinking it's different from the other field, right? So yeah, that's maybe going back to the other field. Yeah,
I'd like to. I just wanted to add something. Diego Mendoza Halliday here, just to respond or to challenge the view of Jim or maybe others that we absolutely need engineering for science, and that we need to build something to really in order to understand it. Let me just bring a challenge here. We might be able to do that in neuroscience. We have the luxury that there's this engineering way to perhaps make something that looks like a brain. But what about the rest of sciences? What about ecology? What about so many other sciences where that's, you know, weather sciences, where it's not even possible to build something? Will you tell all those scientists that they're doomed because they cannot build whatever they study? I want to challenge that and say, yes, it's great to have the possibility to build something and to validate what we're studying, but I disagree that we scientists absolutely need, by principle, absolutely need engineering to understand whatever we're understanding. What do you want to say to, I don't know if that's a valid point.
That's a valid point, and that's a challenge. And again, I'm not trying to dismiss science as a whole. I'm just saying what good science does is build models that explain, that's easiest, predict, that's next easiest, and control. And some science can't control, they can only explain and predict. And you mentioned some, but they better at least be able to predict, or I think they're barely a science, they're a collection of phenomena, right? And then we're lucky that we have a field that actually, we might have the possibility of building stuff that goes beyond explain and predict. In that sense is a more super science and more impactful, and for exactly the reasons you say. So I'm not trying to dismiss other sciences because they're not trying to do that, but I think all science has to aim to predict at least. Otherwise it's hard to, it's a collection of phenomena to start, right? It's pre-paradigmatic in the Kuhn sense, right? So that's, and that's how I would challenge back to it. That doesn't mean you have to build, but you have to aim to predict. And in our field, the things we're predicting are complicated phenomena, so they need complicated models, which means you need engineering not just as a tool, which was mentioned earlier, but as a hypothesis class. The models themselves are hypotheses. And our field has a hard time with accepting those because they're quite complicated. But that's kind of where we are, and that's the only position I'm trying to take at the moment.
Yeah, but Jim, this is generally true for the all of sciences. I mean, there are computers, there are tools, like there are many other tools, very powerful tools. And if you have a theory of geology or evolution, you can simulate your theory on a computer and check whether what comes out is consistent with the data. And the same with the brain. And you know, one of the something we should be careful as computational neuroscientists working between the science and engineering of intelligence is to avoid thinking that the models we are testing are actually the real thing. They are just simulating models of the brain, right? Which may be true or wrong. And
Tommy, I agree with that point. It's not the only activity you want to do, but those models then in the examples you gave, first of all, the question was about geology. Yes, you could build a model of geology, but you might not be able to influence geology even with the model. That was where the question was coming from. But your point of the models are not themselves sufficient, I agree with. But the models also then put together all the phenomena and principles you have and tell you where your theories are lacking, and then that leads to new theory. And that in complex systems, that's the way you have to go. You need that in your toolbox as well. So I don't think we disagree. I'm not saying that models are the only thing you need to do. And I think that's the point we're making.
I want to quickly read a question from the audience. My friend and colleague Tomer Ullman, who's too shy to raise his hand, he writes something. He writes, the main focus of the Turing test was behavioral. So perhaps the follow-up question would be, should the test for human intelligence need to satisfy only behavioral tests, or do they also need to take the algorithm into account as well? And Tomer, if you're still here, maybe you can expand on this. But the question, I think, for the three panelists is whether a Turing test should only concern behavior or should also match algorithms.
Yeah, it's a classic question, and I'm sure that the panelists have heard this before, but it's maybe worth bringing up in the context of all the participants that we have here, which is, again, the Turing test wasn't a test of intelligence. It was supposed to replace the question, can machines think? Turing said, I don't know how to think about that question, I'm going to replace it with a different question, the Turing test. But it's been taken as a test for intelligence, and one of the main focuses of it was behavioral. If you can do this behavior, you are said to pass the test. And a lot of people, philosophers, cognitive scientists, artificial intelligence people said what that is fundamentally missing is the focus on an algorithm. And people like Ned Block made this very forceful argument that you could have a giant lookup table the size of the galaxy. And if that's a giant lookup table that caches all humans' conversations, it would pass the Turing test. But obviously, you know, Ned Block said, this is appealing to his intuition. I don't know if we ran this on Mechanical Turk, but Ned Block said, obviously, we wouldn't consider that as intelligent. Right? This is an appeal to an intuitive theory of intelligence. We wouldn't consider that giant lookup table intelligent. Therefore, algorithms are also important for our theory of intelligence, not just the purely behavioral test. And then a lot of people argued with it, and one of the main counter arguments was, well, you can't build a galaxy-sized brain to cache all possible conversations, right? That lookup table would be insane. You can't do that. There's all sorts of arguments about this, but I think that one of the reasons that this has come back in full force, the vengeance of the blockhead since the 70s and 80s, is that GPT-3 is the blockhead. I don't think GPT-3 is actually a model of human intelligence. And maybe there is in the mind things like lookup tables. Maybe there is in the mind things that are like caching. And I'm sure there are, and I'm sure that they're useful, and I'm sure that they're useful for intelligence in the sense of getting some action done quickly. But in the same way that human intelligence can do 5 times 5 by appeal to a lookup table, you know that's 25 without multiplying it. But you can do 63 times 127 by enacting a multiplication algorithm that isn't a lookup table, and you can have both of these. I think GPT-3 is much closer to a blockhead, to a lookup table, to any of these things. Now, I don't know that for sure. That's one of the problems we have with this. But I think our zero hypothesis should be, for any one of these machine learning algorithms, that if we see it doing the behavior that people can do, is keep in mind that any behavior can be done by multiple algorithms. And our zero hypothesis should be, for all these things, is that whatever it is that they're doing is not human-like intelligence, because every time that we try to tweak these models, push them, try to do generalization, including all the stuff for ImageNet, not just for GPT-3, and there's a bunch of people in the audience who have done these things, they all broke. They all don't do generalization. They all don't do vision. They all don't do language comprehension. So I think it's a possible hypothesis that all this amazing progress that we've been making is to a certain degree building a blockhead. Now, people can retort and say, well, in the mind, you also have a blockhead, and I agree we do to some degree, but I'm not sure that we've come closer with these algorithms to what we would call human intelligence. So I don't know, I've been throwing like a lot of gasoline on some fire right now, but maybe going back to, is a behavioral test enough? Because then maybe GPT-3 is on the right track.
But well, by an algorithmic test, Tomer, do you mean like, what does that mean actually? Because I think some of us in cognitive science, right, like a lot of what we try to do is come up with basically better behavioral tests to get at algorithms which are otherwise invisible. Or neuroscientists like Jim might say, well, no, the way you study the algorithms is you have to study the neurons. And that's makes sense for, but only gives you a certain window on algorithms. And I think those are basically 2 incomplete ways we have to study the algorithm. So do you have one of those in mind, or the other, or some other kind of thing when you say an algorithmic level, Turing?
Who knows what I have in mind? That's the argument, right? But sorry, that was facetious. I feel like I've taken up a lot of oxygen in the room by my questions.
No, it's great.
So I'd rather hear from other people in the panel.
Tomer, can I ask in the meantime? Well,
there's a famous there's an exchange, I think, where Turing asked Wittgenstein, what's your point? And Wittgenstein said, I have no point.
Now, Chris, I wanted to ask Chris whether he can put up a poll asking the audience when they think that Alexa will be as good as the human assistant that you can hire. How many years will it take?
So just to be, so maybe we can put a couple of numbers in there. So 1 to 5 years, 5 to 10,
yeah.
10 to 50, 50 to 100, maybe.
2030, 2050, you know. Chris, can you do that?
So Chris, if you can help us put up a poll about when Alexa will be as good as a human.
Would be at the level of a human assistant.
Is at the level of human system? You mean when it passes the Turing test? You mean?
Well, in that particular sense, yes. I will hire Alexa instead of hiring a person. That's my version of the Turing test.
So while Chris is working on this, Jim and Tommy, do you want to say anything about whether a Turing test should also include algorithms loosely defined?
I think I interrupted Tomer. We can continue now, but I think this question I'm asking is that for...
I mainly wanted to hear from other people on the panel, and not just on the panel. I mean, there's many clever humans here that have lots of interesting thoughts, and I wanted to hear from them.
My answer to Tomer's question would have been, it's just an operational set point. You got to list a set of questions. It's a set of tests. It's never going to be complete. The bigger that set of tests goes, the more constrained the algorithm is going to be to pass them all. And in the infinite limit of a bunch of behavioral tests, you're going to probably be pretty close to a human-like algorithm would be my position on that. You might say, well, you basically built a blockhead. And if that blockhead fits on my phone, well, success, you go, that's going to take over the world in the sense that Tommy described.
But that's a very reasonable answer from an engineering perspective that says, like, look, and I've heard this before from people who say, look, I don't care if you would call it intelligent or not. If I can talk in a Star Trek-like fashion to my phone, that's what I need, and it's worth $1 trillion, and that's enough. And that's fine, but I think this gets at possibly an intuitive theory of intelligence, or I don't know if it's a scientific theory of intelligence. I think that a lot of people would say, look, if you built the blockhead, and I know how it works, and what you've basically built is a giant lookup table, and you've cached all possible human conversations, and you do that by just reference to the lookup table, that's great, it's worth $1 trillion, I'm amazed that you can do that, but I would not call that intelligent. And a lot of people have said, I would not call that intelligent. You might retort with saying, what else do you want? I would call that intelligent, but I think a lot of people wouldn't agree with that. And if you don't agree with that, that's at least highlighting the importance of, it also matters how you get to the answer, right?
Tomer, I think it's even worse than you say, okay? Consider the fact that every behavior, including with time behavior, can be represented as a machine that takes inputs and a state, does a lookup function, and produces a new state and new outputs. Okay, so if you make that function, you can make a good enough function approximation by in fact, for example, storing all the possible behaviors that have ever existed. Okay, you could, which I believe is almost possible with the current network. Okay, then what you end up, I'm talking about the internet. Okay, then you could probably make something that has all the behaviors of a human. Okay, at least that you wouldn't be able to distinguish very much because it would be close to that. And in some finite amount of time, I don't know how long, maybe 20 years, I don't know. But the bottom line is here, would that be something you would think of as being like a human? I say, if it's to me, it's not at all, right? And that's
again.
So you should see a poll on your screen to vote on Tommy's questions. So while people keep voting, we have a question from Ko.
Oh, okay. Hi. I think my question kind of like goes this way. So if we move away from in silico models, imagine like we can look at all the neurons and can manipulate all the neurons of any species, any animal that we can think of, or any living creature. So let's take C. elegans or something. So is that a good endpoint? So let's say we have this technique now where at any point of time, we can record activity of all neurons of a species, or we can manipulate the activity of all neurons of a species for any kind of stimuli you want. Will that be a good endpoint to an endeavor of science or engineering for that matter? Because I feel like if there is still something more we want to do,
Sounds
for example,
more like a good starting point than a good end.
I understand. Yeah, exactly. But I feel like that would be the end point to some extent of the way the conversation was going. Like we build a system completely replicating, the system that we want to understand. But then if we still want to abstract away from the real system, then I feel like that's kind of not where I at least thought initially where we were going. Like then it feels like, okay, there is something more to understanding, quote unquote, more than just building the system that predicts and something that we can control. It's like trying to build some sort of like algorithm.
So are there general principles
exactly
of explanation other than, I mean, I think here Tommy and I, if you want to talk about the panelists, Tommy and I would say unequivocally yes. And I'd love to hear Jim's answer. I think, well, I don't know. I mean, because Jim, of all of us, at least, he's been the one most arguing that like the big model is the understanding. But Jim, you tell us what you think.
So Jim, you have to go now. So maybe you answer this question and a few parting thoughts before you leave.
My parting thoughts of this has been fun, but I would just, my quick answer is, Josh, it would like, at least building it would be powerful to do a lot of things, but I hope.
Yeah, absolutely. Right. Is it necessary or sufficient?
That there's principles underneath, and if they're there, there'll be shortcuts and they'll make things more efficient. And that would be really nice if it was true, but we have there's no guarantees on that is the only thing I would add. And I would also add, related to that, you gave up brain disorders earlier as, oh, we don't need this models for that. That is, I don't think you should give that up.
I didn't say that, or I didn't mean, sorry if I was just saying some people who study that may not need, no, I mean, right. Yeah, it's, I agree. I think,
Okay, so
be that. Sorry, I gotta run. Thank you guys.
So thank you very much, Jim. I know that you have to go, so thank you very much. That was great. For those of you who wanted to know when Alexa will be at the level of Tommy's assistant or any of our assistants, the answer is very clearly and unequivocally 10 to 25 years. That's when that's the mode of the distribution, at least. Maybe
it's also an interestingly broad mode.
It is pretty close to a uniform distribution. That's very true. So I want to ask at this point, maybe also to Josh and Tommy to have some parting thoughts on this topic.
Sure. I mean, okay. Well, I guess I can say a couple of things. I mean, just to finish on what Jim and I were both saying. I mean, I think so. Jim said there's no guarantee that there'll be any principles. Yeah. I mean, I guess there's no guarantees in life, certainly, or in science. But I think most of us are committed to the idea that, like, we won't be satisfied, at least, unless our science leads to general principles, a unifying theory in the way that science has always looked for, in addition to the kinds of engineering models that we're talking about. But, you know, it could turn out to be, it could not work, but I think that's what we're aiming for. And I think aiming for that has always served us well, whether it's to make more efficient models, as Jim is saying, or more efficient model building, or a lot of other things, or more flexible, generalizable toolkit for modeling, just as abstract knowledge helps human intelligence, not just in science, achieve flexibility and generality. I guess I would also just say one other thing that's just a reflecting on a comment that Paul Smolensky made at a workshop connecting AI and cognitive science that a number of us were at. I know Tomer was there, and and maybe some others here, which was very telling, and also speaks to the difference between science and engineering, but where there is sometimes a tension, but often a productive one. This was a workshop that was specifically, well, a lot of the interest was on cognitive development and, you know, can we build models of intuitive physics or language that learn the way human babies and children do, or can we use AI to reverse engineer how human children learn common sense and language? And as often happens when AI people and neuroscience and cognitive science people get together and debate that, one of the things that comes up is that people on the AI side, especially, as well as some people in neuroscience or cognitive science, are very drawn to an approach which is like kind of learn everything from scratch. Like the thing that makes the model, the best models are the ones where you build in the least amount of structure or the least amount of knowledge, and then they learn the most out, right? And that's what you should be striving for. But many people in cognitive science, as well as neuroscience, have a different goal, and they say, well, no, what we should be trying to build in is what actually is built in biology. You know, our genome builds an incredible amount of structure about, you know, the structure and function of the brain, the learning algorithms, as well as, you know, in some ways, concepts and conceptual representation. And that's a lot of what the study of very early infant cognition has suggested. So there was this tension between people who were basically trying to build in as little as possible, and like the less you built in, the more you got out, that was just assumed to be better, versus people who were trying to figure out what, you know, build in like the key pieces that seem to be built into human babies. And in a moment of some tension between people there, Paul Smolensky, who, if those of you who don't know him, he was a physicist originally, and then a computational neuroscientist and linguist, and he mostly works in linguistics right now, but using neural networks. He's one of the people who's most advanced creative ideas of neural networks and language, but also very much guided by what we know about human language. Anyway, Paul said to one of the machine learning speakers, he said, "Are you trying to do something cool, or are you trying to do something real?" And this was him, I think, encapsulating the difference between science and engineering. Now, it was a little disparaging the way he put it, but I, as someone who's on the science side but very interested in engineering and very appreciative of engineering, I see what he was trying to say. That it does seem like, and going back to what Jerry said also in terms of, like, you know, engineering, in science you're trying to understand something that is, in engineering you're trying to build something that has never been, and that's amazing and awesome and impressive. But how do we, you know, what are the things we're trying to build? Well, we might be motivated by societal applications and making the world better. And it would be great for AI to be more motivated by that when people try to say, what should we build that has never been before? But often these days, AI engineering has just been motivated by some sense of what would be cool. And given how powerful learning systems have been, the cool thing is to show how much you can get from the data without building stuff in. Whereas I think the scientist has a really healthy perspective on that and says, okay, well, maybe that's cool, but I want to know what's real. And I want to use engineering tools to better understand what's real. And I think that's not only the right scientific goal, but also one that will help to advance and fundamentally advance AI, because we look to human intelligence and we still see something that is, by whatever we mean by intelligent, and I go back to the definition that Tommy really usefully introduced when we started the intelligence initiative. You know, look to the Latin. Intelligence means to understand, right? Intelligere. So by any notion of intelligence, you know, just what does it mean to, what does it mean for a system to understand the world? We have really only one good example of that, which is the human mind, okay? And the human brain as it implements the human mind. And the science that we do in CBMM and in all of our work, and the scientific discussions we're having here, are one of the best, most salient examples of human intelligence at work trying to understand the world, including itself in the world. So if AI is to really have a future, and an inspiring future that is also where it came from, right, in the early days of the field, it is going to have to look to what is real, not just what is today's momentary sense of what is cool. It's going to have to look to what is real in intelligence and be guided by that. And I think all of us can gain a lot from that perspective, whichever side we're on, as we work at this joint enterprise together.
Thank you very much, George. That was very nice. That was great. Tommy, final thoughts?
Yeah, just very briefly. You know, a pitch for CBMM. CBMM was born with the belief that the engineering of intelligence must be complemented, not replaced, but complemented by a scientific investigation of the only example that we have of natural intelligence, which is Homo sapiens. And I think it's only if we understand better the biology of our own intelligence that we'll be in a situation to understand the promises and the pitfalls of AI when it will be better than it is today. And in short, I think, you know, there are probably 2 or 3 order of magnitudes in terms of money and people that goes into the engineering of intelligence compared with the science of intelligence today. And I think that this effort, which is great on the engineering of intelligence, really calls for an equally grand and synergetic effort on the science of human intelligence. So that's CBMM. And I think there is more work to do beyond the first 8 years.
Very good. So thank you very much, Tommy. That was great. I want to thank both Josh and Tommy and Jim, who's had to leave now, and also all the people who participated through your questions and all the comments in the chat, which are also great. I'm sorry if we didn't get to your questions. Thank you very much for participating.
Well, thank you, Gabriel.
Yeah, thanks, Gabriel, and thanks everybody for participating.
Yeah, thank you.